Okay, let's get started. So from last time, we started looking at storage, right? So last time we started looking at we started to look at storage. And when we look at storage, we'll continue to do this class. And we'll look at basically, all kinds of different battery storage technologies and think about which ones are better, which ones are worse, which ones are suitable for other, for different applications. It's worthwhile to keep in mind that in power system, we have some form of storage. Okay, so it's not like today's system or the conventional system, we never had storage, right? So the key thing to remember is, again, you can think about the system in terms of time scale. Okay, so let's say this is 10 milliseconds, 100 milliseconds, seconds, 10 seconds, hours, days, well, something longer than that. Okay, so this is sort of a very useful tool to think about different phenomena in the power system, right? So if you look at storage, we actually have fairly, fair amount of storage here. And this is represented basically by mechanical inertia, right? Okay, so again, if you went to the seminars this quarter, you heard about this again and again. Thus, the mechanical inertia is the inertia that's in the rotating machines, right? Rotating machines. These are big machines, and they have a lot of energy storage, actually. There's sort of significant amount of energy stored in the machines. But they show up in a time scale, let's say of sub-second time scale, right? So for sub-second things, you have the storage inherent in the system because we use synchronous machines. And these are present, and a lot of stability issues in the stability of the power system is basically controlled or helped by having the sort of machines. Okay? And then, so these are already there, right? Where we have this storage. Now with renewables, we may be having less of this form of storage, but that's but still we have a significant amount there. Then if you look at this time scale, we also have sort of fair bit of storage. We have some storage in this time scale, right? In the sort of days time scale. You might think of what that is. That's already in the system. And you think Washington, we have a lot. The state of Washington has a quite large amount of storage in, let's say, the day and the time scale longer than day, right? So such as this is hydro, right? So this is hydro storage. Basically, this is the storage you have by pumping water up a hill, right? So you take the gravitational energy, the potential energy, which is how you store power. Okay, so this is the storage we have in the system. So these are already there. Okay, these are already there. And depending on where you are, you may so we have mechanical inertia. And hydro, depending on where you are, you may have a lot of it or not too much of it. So Washington, has a lot. Another example is, for example, Hydro-Quebec in Canada. They have a lot of hydro, right? Some places, for example, Texas, may have less hydro storage, but these are the form storage we have. So what's in the middle is what we don't really have a lot of. Okay, so if you look at a lot of storage technology we're talking about, it's worthwhile basically to place them in this time scale. Okay? Think of several seconds to hours. This is a question, okay? We don't have, or traditionally, we did not have this type of storage technology in the grid. Okay, so before we had, very short time scale, that sort of mechanical stuff. Very long-term scale, pump hydro is old technology, sort of obvious technology you want to use store power, but that's there, but that's sort of very dependent on where you are, whether you can tap into that or not. And in the middle is really something we're looking for now. Okay, so when we talk about storage, in the last few lectures in this class, think of this time scale from a second to say a few hours. Okay, what kind of technology do we have here? And what kind of applications do we want them to serve? Any questions about this? Or the time scale? Okay, so this kind of separation of time scale thinking is actually quite useful to have in power systems. It's a quite useful picture to have in your mind. So where, at what time scale are things happening? Okay. Right. So the reason you need something, right, in the sort of 1 second to hour time scale is a lot of it is because of renewables, right? So renewables, last time we also went, covered this a little bit, is renewables has a lot of uncertainty, right? So a lot of variation in their output. For example, this is a good solar day. Basically, this is a very stable output. I think this is somewhere in California. So this is a very stable output of solar power you get from a farm. Okay. So almost flat with little bit of wiggles, but no big change. But then when you look at it's the same wind farm, let's say wind farm, a few months later, you basically run into this kind of drops. Okay, so you have a huge drop like this. This goes on for about an hour. Okay, so this is roughly 1 hour. Right, so we have this kind of drops in the output of the solar generator, of the electricity being generated. So this is this basically is why, right? So if we have something that's over an hour long, then basically you can smooth out. This also says, if for solar, if you select the right site, right? So another way to think about this is, we may want to smooth out this output on an hourly basis, right? Because if we can smooth this out, it's much easier for the system to work with, right? So if there's sort of longer term drop in output, that's also not too difficult to deal with if you can plan for it. And so if you can plan, let's say, for the solar cell not to produce power for an entire day, that's also okay. We can do something else. What you're afraid is actually this sort of sub-hour drops, this sort of huge drop in power that lasts for, let's say, up to an hour. That is hard for the system to react and plan for. Okay, so storage, we can think of, right? So remember your filtering. Essentially, what a major application for storage is to filter this. Okay, think of the storage as a filter, low pass filter, and your goal is to filter this signal to make it much more smooth looking. Right? So I want to run so the system really want low pass signals, right? So you want storage, I'll act like a low pass filter for this. Then when we think of storage, right? So at the first approximation, when power system people think of storage, what we tend to think of storage as sort of a naive model for storage. It's just basically as a box, right? So that's a naive model for storage. And we'll have power in, power out, and there's some finite capacity. So this is sort of our naive way of typically, right? So thinking of a storage, it's just a box to store power. Now, of course, there's some upper limit to how much power energy this box can store. But then otherwise, it's a box, right? Sort of this perfect box. So a lot of early studies was done with this kind of black box model for storage. As you look at your battery, you say, okay, this is how much megawatt hour you can store. This is, so you can plan things with the battery. So this is sort of black box model. This is used in early studies. Actually, it may not be that early. So this sort of 20 years ago, you'll see a lot of storage saying integration of storage is basically a box. Okay, storage is box. So, once we, made a lot of studies with this kind of storage, then we figure out, no battery storage actually look like this. Okay, battery storage simply do not like an ideal box. Right, so in this, this lecture, our goal is to look at some of the non-idealities of this and look at different technologies, right? So what is actually going on if we go beyond this box model, right? So right now, any drawback of this model, right? So what are some of the practical considerations for storage that's not modeled by just saying this is a box? Can you think of any sort of practical constraint we have to take into account?
Power losses in the storage.
Right, so one is power loss, right? So we have, sort of real battery or practical. Right, we have power loss. Right, so if you just sit there, it still loses power. It's not a perfect container for power. So right, so we all know this, right? If you have a cell phone, you don't charge it, for a long time, even if you turn it off, the battery drains. Right? So anytime you have, wires connect to it, you'll drain some of the energy away. So that's power loss. What are some of the other things? Right, so it loses power by sitting there. What are other sort of non-idealities that we take into account? Power loss turns out is not very hard to take into account. This is not a limiting factor for when we want to model storage. There are some more limiting factors. Power loss is not quite limiting. Anything else about a practical storage? What also might happen? We have a practical
loss of capacity over time, like from multiple cycles.
Right. So degradation is more important. Or let's say capacity fade. Capacity fade. The capacity fade is as the longer you use the storage, the less capacity you can store. So that's a major issue in storage, right? So whenever, for example, for our phones, a phone that's 2 years old just have a smaller battery, right? Just appears to have a smaller battery than a brand new phone, right? So that's capacity loss. So that you can think of this is sort of similar in some sense to the mechanical stress that you put on let's say metal. Okay? It's very similar to that. So if you have an airplane, you keep flying the airplane, you have put on mechanical stress to it, and eventually you reach a breaking point. So capacity fade is similar to that. As if you keep using it, you stress the battery, and the capacity reduces. The difficulty with this this type of phenomena, this is a very complex. This is a complex phenomenon, right? We don't really have a very good idea of, we have ideas, but it's hard to say in practice how much capacity you left. And so you look at a lot of the, for example, you look at our buses, so King County buses. A lot of buses now are hybrid, so they have a battery. And often the question is, after I drive this bus for 2 years, how much capacity do I actually have in my battery? That's actually not very easy to figure out. Similarly, in your phone, right? So your phone will have an indicator saying, how much battery you have, how much time you have. But that's actually a very crude estimate of the true capacity in your battery. Okay? So the true capacity of battery is actually not easy to figure out. Not all that easy to figure out. Okay? Any other considerations we have? So we have power loss, we have capacity fade. How about one more? Think of one more practical reason. So anybody remember when the Boeing 787 first came, so went into service? There were several fires on the plane. Anybody remember that story? If you think back to, let's say, 4 or 5 years ago, there was, right? Yeah, so thermal runaway or safety issues, right? So lithium ion, this sort of more particular to lithium ion. Lithium ion has the unfortunate property of catching fire sometimes. Right? So that now later in the class we'll see a little bit why this is the case, but there's safety issues, right? So now sometimes when you want to put a storage, let's say in an apartment building, you actually there's a code of what kind of storage you can put in, and sometimes you're not allowed to put in a storage in an apartment building because the code doesn't allow it. You have to say what you're gonna do if this thing catches fire. So for UW, a couple of years ago, I think we had a storage. We tried to put in a student dorm. That was no because of this issue. We have to. There's a fire hazard. Basically, it was considered as a fire hazard to have a storage in your basement if you live in a dorm. Right? So these are sort of the practical considerations that doesn't go into the perfect black box model. Okay, so this class will look a little bit why, why does this for non-ideality, where do they come from? What different technology do we have? And then next class, we'll take a more sort of system engineering perspective on, to think about how should the storage operate. Okay, so that's sort of our idea. So if you look at the storage technologies, right? So broadly speaking, right? So again, the first we have and the largest scale we have right now is pump hydro. That's economical. If you build a dam, but this is geographically constrained. And most places in the US has tapped this out already. So we have pretty much tapped this out. Then we have sort of phasing out. We're slowly to phasing out lead acid. So lead acid are your car batteries. We're slowly started phasing these out. These are not very friendly to the environment and sort of hazardous if you open the battery up. Right? So we're phasing this out. Then, of course, the most common we have today, in our phones and our computers, in the electric vehicles, is the lithium ion. Lithium ion. Right. Can you think of some other types of battery you may have heard of? Right, so these are the common ones, right? Lead acid, we all have seen, that's in your cars. What do you mean by solid state? Right, so lithium ion is sometimes called solid state, right? So that's for lithium ion. Right, so molten salt is really not a battery. It takes a while. That's sort of more like a fuel in a battery. It takes a while to get power out of that, right? So that's sort of not really a battery technology per se. So redox flow is a battery technology. So redox flow is actually quite competitive, so these two are sort of the most competitive. We'll go into what a redox flow is. Actually, you have never heard of this. Gas electrolyte, right? Yeah, there's some like that. Not very common. Then some of the others are, for example, we have things like flywheel. So this is exactly what what the name says. Flywheel, we have supercapacitor. Right? So these are, some of the common ones you can buy. Right? So today you can definitely buy lithium ion, redox flow, flywheel, supercapacitor. You can buy them off the shelf. Okay? So these are all there. Some of the ones that sometimes cause storage that we're not going to think of storage in our system, as for example, hydrogen. Okay, so this is fuel cell. Right, so there's getting a lot of attention for hydrogen recently, and sort of justified attention for hydrogen. But we're not going to think of hydrogen as a battery, because really you're converting electricity into a fuel, right, which happens to be hydrogen, and then you can generate power through a reaction of hydrogen and natural gas, let's say, to create a fuel cell. Right? So that's really, it is energy storage, but that's typically not what we think of in the grid as energy storage. We are not think of fuel cell as storage. Because to use fuel cell, for example, you also need natural gas, right? If you want, so one type of fuel cell is you need natural gas supply. Right? So that's so that's sometimes not. But where the others is basically electricity in, electricity out. So that's one type. And then, for example, other thing we said is sort of molten salt. So there are storage, right? It's power in, power out, but they are sort of, there's a few conversion process going on, right? So which is they're a little bit outside the scope that we can treat in this class using engineering thinking. Okay. So all these are, viable technology, right? All these are viable technology. It's unclear which will win out at the end or would have a mixture of these. So there's definitely proponent to all this type of, for each of these things, right? There are people who really believes in lithium ion. There are people who really believes in redox flow, flywheel, supercapacitor, fuel cell, etc., etc., etc. So when you go forward, maybe it's good to for us, right? We're not making batteries, right? So we're electrical engineers. We're not making batteries. We're gonna use them, and then what's to keep in mind is what's the characteristic of each technology, right? And not so we're not constrained to one technology, right? So we're making a fuel cell, we may believe in that, but for us, we just need to make use of them, right? So it's a good thing is keep in mind what are their characteristics and why they may be good or bad for some applications we may have. Okay. All right, so let's quickly go through these different technologies. So this is a flywheel. A good flywheel is basically what the name says it is. It's a big spinning wheel. Okay, it's a big spinning wheel. This stores power as mechanical energy. Basically, you put in power, you spin a rotating mass, and if you need power from it, you can get power out of it. Okay, so this is a flywheel. Okay. Flywheels. These are used sometimes, right? So these are sometimes used. When you need to store actually a lot of power very quickly, the bad thing about this kind of technology, since they're mechanical, there are always losses associated with it. The rotation loss can be quite high. So you're basically looking at applications where it's a very rapid discharge of power, so that can happen. Then we have compressed air, right? We have compressed air. Compressed air is you store compressed air underground. Now you can, again, sort of pull power out of that way. But this is more aligned with more similar to molten salt in some sense. Right, so it's not terribly fast. You can't get power terribly fast, but compressed air is a good storage technology. For example, over several hours or over a day. That's a possible technology. So let's go to the one we're most familiar with, which is lithium ion. Okay, which is lithium ion. So lithium ion, basically, the name comes from, we used lithium. Lithium is the anode, basically, of the battery cell. And the cathode, there's a lot of different cathodes in the cell. Okay, so the way this cell works is, you have a cell, you have a power, you have a flow, right? You have an anode, you have a positive terminal and a negative terminal. And what happens as the lithium ion flows in the cell, and this is, we can have different cathodes here. Okay, different cathode, different negative terminal out there. And this gives us name. Okay, so when we say lithium ion is actually a family, so a large family of batteries. Right, so I don't pretend to understand why what are these materials or what they do, but they basically have different applications. Okay? So what we have is, the most common one is carbon dioxide. So these are the ones in your phones and your laptops. Okay, so you want a short story, these are the phones in your phones, laptops. Okay? These have very high specific energy. Anybody remember what specific energy means? And so often when we talk about battery, we'll say what the specific energy of a battery is. Anybody remember from physics, chemistry, or can guess what this means?
Energy per unit mass?
Energy per unit mass or per unit volume. So this is normally energy per size, depending how you exactly count it. Right? So specific energy, this is energy per, let's say, size, right? So depending on whether we're weight constrained or we're sort of size constrained. So the reason we use using laptops and phones is obvious, right? We're limited by size. It's how big your phone can be, limited, a lot now is by the batteries and the electronics around the battery. So you want it as small as possible, high density. Okay. And they have, small batteries tends to be more prone to catching fires. There's reason for that. We'll get into that later. But so these are the ones we have now. Then if you look at things like EVs or bikes, we have sort of this high power output. Then you can trade off a little bit of the specific energy or specific power with safety. And there's all kinds of different materials, cathodes you can make. Right? So these are the second class of batteries. And then the last one is the last two are a little bit new, but then they're also becoming to market. So most of these different technologies are in the same family, right? There's a lithium ion family. But by making the cathode to be different, so you can search over a very wide range of behavior. And the people who make batteries basically worry about, they try to come up with new technologies of different cathodes and what to make. So when you go out and buy lithium ion, there's a big choice, or there's sort of big, wide variety of technology you can choose from, right? So sometimes it's important to figure out which one of these, you actually need in your application. Okay? So are you limited by size? Are you limited by power? Are you limited by safety? Things like that. So for example, this is the actual battery we have together with Snohomish PUD. And this is a lithium ion battery, and this is installed as part of the microgrid. This is a part of microgrid. So these batteries, this is much bigger. It's much bigger than your battery in your cell phone. So I believe this is in the megawatt hour range. And what you're looking at is basically an empty parking lot, and we're installing the battery at the parking lot. So what this outside is actually the container. Okay, the container. So these batteries sit in the shipping containers for safety reasons. Okay, so they sit in a container for safety reasons, and there's wiring around inside the container, and then battery sits inside. So if it happens to catch on fire, it's contained, right? So somewhat contained. And this is for a microgrid. So you can think of the battery of this size powering, let's say, 10 buildings, right? On the order of 10 buildings or so, a battery of this size. Right, so the way we got to buy this battery, actually, when you want a battery, the vendor typically give you a lot of choices. Okay? So it's important to understand what kind of technology, what kind of choices we have in buying the battery. Okay, so now let's think of a little bit sort of detailed description of the battery. Okay, let's think of a little bit more detailed description of battery. The first characteristic we care about a battery, is something called the C rate. Okay, so this is so battery has this physical size, right? So battery always comes with a physical size, but sort of the electrical property of the battery or the energy property you can think of is something called C rate. And so this is basically the charging rate. The charging rate of battery. And this charging rate is computed in the following way. 1C charging, this is the battery charges to full in 1 hour. Okay, so C rate. This is 1C rate, as it takes 1 hour to completely charge the battery. Okay, so this is what we mean by C rate. Okay. And others, right? So besides this 1C rate, now we can define different C rates. So normally with this comes in an integer. So normally what you have is you have Kc. Okay. So Kc, this means that battery charges to full in 1/k hours. Okay, so this is just what it means. Okay, this is, sorry, not in 1. Yeah, 1/k, 1/k hours, 1/k. Okay. So a higher C rate means you charge faster. Okay, so a lower C rate means you charge slow. So for example, another common we'll see is we have 2C rate, means we charge, so we'll fully charge in half an hour. Another you also commonly see is 1/24C. This is fully charged in a day. Okay, so this is a common characteristic. So this is an important characteristic of your battery is how fast can I charge it, right? So how fast can I charge it? So what controls the C rate, right? So there's two things that controls the C rate. It's basically the degradation, right? So how much capacity, so the faster you charge it, the more stress you put on the battery. So the battery dies faster. So that's one important factor that goes into how much, how fast you can charge a battery. Another consideration is safety. Okay, try charging a battery too fast, something catches on fire. Okay, so the C rate is, we have technology, basically is determined by the degradation characteristic and the safety characteristic. So the safety characteristic is hard-coded into the battery management system. For example, you take your phone, there is an upper limit to the C rate it will charge at. You cannot actually get it to charge faster than that. It's very difficult to get it to charge faster than that. There is a logic, right? There's a management system sitting outside the battery limiting how fast you can charge. And if you have one of the newer phones, for example, iPhone, then you may see this kind of message on your phone, right? That says, oh, I know, you're going to start plugging this thing overnight. So we're going to charge slowly and the battery will charge by 4 a.m. in the morning. It takes 6 hours to charge. So you may see this kind of thing on your phone, or you may see this kind of the message in your computer saying, you're not using power, so we're not going to charge very fast. That's basically you adopt a slower C rate, and that is better for your capacity. Okay, that is better for your capacity. Right? So this is. Okay. So you may see, you may see your phone claiming, oh, we're figuring out this by AI or something. It's actually not that fancy. It's basically you take a bunch of phones, you try different rates, and then sort of you figure out what's a good capacity, right? How does the charging rate correspond to capacity? Okay. So you have, a lot of new technology, new batteries control C rate. Okay, so C rate is important. And when you buy something, sometimes you want a fast C rate as a maximum rate, right? So for example, if you have an electric vehicle, you bought a supercharger, you want it to charge, let's say, in an hour, right? I want my Tesla to be charging an hour. Okay, so you may insist on that being the maximum C rate allowed. And then if you plug in overnight, you may allow a sort of slower charging, it's smaller C rate. Okay. Any question about this, about the C rate? So this is one of the sort of most important characterization of a battery. Sort of what's the max C rate, right? What's a nominal C rate you should operate at? Okay. Questions? So any guesses for the battery out there? Are we above 1C or below 1C for most technology? You will see. That we will sort of touch day to day. Do you think for the most battery, look around, you have, are they, above 1C or below 1C when you plug it in to charge? Below, right? So most of the battery is sort of below 1C. Okay, so 2C rate is actually very fast. It's rare to see something charge at 2C rate. Yeah, it's quite rare. It's quite rare to have a charging rate at 2C. That only happens if you have a small battery, actually. Most times it's sort of below 1C. So half C is common, 1/10C is not uncommon. Okay? So you have this kind of different charging rate. Right? So when you buy a battery and you want to charge into full in an hour, there may not be that many batteries that can do it. Okay? So we have application and your demand is, I need my battery to be full in an hour, then sort of that limits your technology choice. Okay? So the way this works is basically, so how do we control the C rate? So let's look at lithium ion for now. Let's not look at the flow. Right, at 1C, basically what you do is you charge at higher voltage. Okay, the way you control C rate, if the battery allows you to do it, as you control the voltage the battery sees. Okay, so you need to charge at higher C rate, and the battery is, you put a higher voltage across it. Whereas a lower C rate, you put a lower voltage. So the red is, right? So the red is voltage for 1C, and the blue is voltage for 0.2C. Okay, so 1/5C. And this is controlled by the power electronics you have on board. Okay, so this comes back to power electronics. The way it works is you have a BMS, you have a management system, looks at how fast you want to charge, and then the power electronics converter. Let's say you have a buck. You have a buck converter, and the buck figures out the right voltage that appears at the battery terminal, and that determines the C rate. Okay. So so again, all these things are related, right? So to do this, we need power electronics that can change voltage. Okay, so your buck converter, right? So all your phones, all your computers is actually has a buck converter inside, and sort of dynamically changing the duty cycle to charge at the appropriate C rate, charge at the correct C rate. Right, any questions about this? Okay, so this is sort of the limit, right? So this is the important limitation for us for a battery as a C rate. And then some of the other consideration we have when we operate the battery are the following. So we're modeling a battery storage in a system, right? So if you, let's say you buy a battery technology and you want to model it in the system, then what happens in the system is basically you have to put this as a model in the system, right? If you want a battery, then it has to appear as some component in the system. And if it's generating power, you may want to, appear as a generator. If a consuming power may appear as a load in our optimization problems. So the normal modeling for our battery are the following. So normally there is no minimum generation, mean load, startup, startup or shut off constraints. Okay, so when we model a battery, right? So how is battery different than, let's say, a generator? Well, for generators, you have minimum generation, you have minimum load, you have startup, shut off constraints, you have all that. Whereas for a battery, there is no, we don't have these, right? So there's no minimum generation of a battery. There is no minimum amount has to consume, right? And there's no startup, there's no startup shutdown costs. Okay, so we don't model these. And then another consideration we have is ramping, right? So how fast can you charge up and down, right? How fast can you ramp up and down? This is sometimes important, sometimes not, right? Sometimes not. So this is only used if the application is in seconds time scale. Okay, so if you're talking about seconds, then how fast you can charge or discharge will come into our consideration. Otherwise, if you talk about 5 minutes, a battery at half a C or 0.5 C will not be power limited, will not be limited by the amount of power it can output. Okay. It will not be power limited. Then we can look at things like operating cost, operational cost. So what kind of operating cost do you think we have in managing a battery? Right, so let's say I buy a battery. Let's say I buy a battery. The operating cost means the day-to-day cost of running the battery. What kind of day-to-day cost do I have? Right, say our building, the ECE building, we decided we want to putting a battery in the building. Right, let's say somebody donates a battery to us. So, but then what kind of cost do we have in running the battery, actually? Is it actually zero cost? Is the operational cost of battery zero? Is it something like one? You buy it and then it's just there? Or is it cost actually finite cost, not zero cost? Need to buy power to store, that's true, but that's for the, right, so that depends how you use the battery. That's depending how you use the battery. So buying and selling power will take it into, will sort of set that aside, because that's sort of operational control. That's the control we have on the battery. So let's say other than the cost, putting power into the battery, what other costs are there? So of course, putting power into the battery costs some money. Using the power can, give us, earn some money. So other than that, what other costs are there for running a battery? Right. So one cost we have is AC cost, actually, air conditioning, because you don't want the battery to run very hot. Okay, that's also not good for safety. So air conditioning. Okay, so batteries actually need to sit, normally sits in the air conditioned room. or climate control route. So if you go to, for example, as I said, a data center using battery as a UPS, then if their topology is you have a big UPS at the front end, then that's just in a climate control route. They have to cool it, right? So this is sort of actually the actual money you have to pay to operate the battery. This is additional AC cost, air conditioning cost. Another cost when you operate the battery, this is degradation cost. Right, this is basically the charge and discharge. This will reduce capacity. Okay, so you bought a battery, and then after a year, it's sort of 90% of the old battery you have, right? So this basically you can think of as an operation cost. Anytime you use it, there, some little part of your battery disappears, basically. And this is different than charging and discharging power, because, right, so that depend on the market or depend on the payment scheme you have. You can make money that way. But degradation is just anytime you use it, the battery just small percentage of the battery disappears and it's not there anymore. So that's a operation cost. And then we can think of the constraints. So constraints we have, there's a power rating. So this is similar to ramping, right? So this is similar to ramping. And this is the power electronics control. Okay, so this can actually use the power electronics sets a power rating in the battery. Right? Power rating means can you go from off to providing, let's say, 1 megawatt very fast. Right? This is sort of power rating. Or at any time, can you what is the maximum power you can output? What is the maximum power you can output in the battery? And then we have the energy rating. Energy rating is just how much energy you can store. So this is, for example, something in kilowatt hours. This is something in kilowatts. Okay. So they are different, right? Kilowatt hours and kilowatt watts are different. So a battery can have high energy rating and low power, or high power and low energy. So both are possible. Right? So when we use a battery, normally we need to take all this into consideration. Okay. So we have to be mindful of these are the things we have for our batteries. Any questions with this? Okay, so if no questions, let's take our break now. Then at 1:31, we will resume looking at battery sensor. How do we do problem formulation? And and later we'll look at a few more technologies more in depth. Okay, so let's take our break and come back at 1:31. Okay, let's get started again. So one thing that we need to look at when we model storage, right? So is to look at the operating cost. So for example, the cost, additional cost from climate control or from air conditioning, that's fairly easy to handle. Okay, so that's just additional megawatt hour you have to buy electricity. But how do we think of degradation as a cost? Right, so degradation, remember, is reduction capacity. Normally, that's hard to work with directly, thinking about percentage reduction. So when you solve any problem, you want that to turn out as a cost measured in, say, monetary values, right? So dollar per something. And so the way that this is turned into a cost of dollar per something is the following way. So a simple way to do it is the following. As when you look at a battery or lithium, especially lithium ion battery, most battery will come with the information that this battery can operate, X number of cycles. Okay, so for example, I have a lifetime of, let's say, 10,000. 10,000 is a lot. So 5,000. Okay, 5,000 cycles. This means if you charge and discharge the battery 5,000 times, then you should throw the battery away, right? So that's sort of normally what this means. So I noticed, so what does the end of lifetime for battery mean? Then the capacity goes to 0? Right, so what actually is a capacity where we declare the battery is dead or the end of life? Right, so we start with battery 100% capacity. At what time would we consider this a dead battery? Or a battery that surpasses lifetime? Yeah, so right, so 80% is correct. So this is for 80%. Right? So when the capacity reaches 80%. Okay, so this is obvious. This is actually a high number. And most other things, we don't think the resource being completely exhausted at the 80% of lifetime. But for batteries, we do consider at the past its lifetime is at 80%. So the way you can break into this is, right? So the way you can break this into a cost is, let's say a charging. This charging is similar. A charging of, let's say, X happens. Right? So the cost you associate with it is X, right, over the capacity. Right? So how much you charge? Let's say you charge 10% capacity. So this X over this is 0.1, right? X over capacity times the battery cost over the fact that you can go 5,000 cycles. Okay. So this is a cost of doing charging X. Right? So charging X units. Okay. So this is, for example, you have charge 10% of its full capacity, so that's 0.1 times the cost per cycle. Right? So this basically tells you the cost per cycle. So this is an easy way to account for capacity degradation. Right? So you can, and all this information is available when you buy a battery. You know the cost of battery. All batteries now will tell you how many cycles they can undergo. And that's sort of information you have for all of them. Then you can figure out how much is the cost for one action you take. Okay. And then this is not very accurate or very realistic, because in actual practice, the cost is not linear with respect to cycle depths. But for now, we will think of this as, for now, we will ignore that. We'll ignore sort of the nonlinear part of it. I think, if it's just linearly proportional to the cycle depths, and this is the way we'll account for cost. Okay. So this is, so in practice, it's actually nonlinear, but here is a linear cost. Okay, so but we're here thinking linear. So actually, this week we'll have a homework as well. So we'll go through some of these. It will be a short homework. So this week we'll have a short homework with 3-4 questions, and looking at some numbers associated with this. Okay, so well, what's the typical cost of battery, and how many cycles can go, and so what is charging to half full. Okay. And so battery loss, battery degradation is in itself a complicated issue, complicated question. And this is a very active area of research, very active area of work, right? And none of this is simple because one reason is actually it's very hard to measure capacity of a battery. So let's say you have a battery. How do you think we measure capacity of a battery? I think that's actually interesting to talk about. Right, so let's say you're making a battery. How do you think we actually measure? Right? It's important to know how much. Right, so it's important to know how much the power or energy battery can hold. So that's capacity, and the capacity changes as you keep using the battery. So how actually do we know? Right, so just as test discharge. So can you be more specific? What's a test discharge?
Like discharge the battery at a specific rate and see how long it takes.
And what rate is that? It's close. What do you think the rate is?
I'm not sure.
Right, so the most accurate way, accurate measurement. Okay, so you cycle the battery slowly. Okay, so this test cycling, you cycle very slowly. For example, 1/24C. Okay, 1/24C. So that means you take a day to charge the battery, take a day to discharge the battery. And then because this is cycled very slowly, you can actually read out how much capacity you have. Okay, so this is sort of the slow cycling. So if you're familiar with for example, the Clean Energy Institute test bed, we have batteries. So this is a test bed or behind U Village. We have a building there. And in there, you'll see people, you see battery cyclers. That's right, it's a box, it's sort of a chamber. You put the battery in there, it'll cycle very slowly, okay, for you. And you can do detailed characterization this way. Okay, so very detailed characterization. Okay, so this is obviously not doable, in an application like your cell phone. Okay, you cannot leave the phone there for 24 hours doing nothing except sucking a battery. So what is a less accurate but maybe easier way to do this? For example, how does your computer or your cell phone, your electric vehicle know how much capacity you have? What is the power cost function? Seth, can you elaborate on that a little bit more? Okay, so the sort of more practical. Oh, so running the motor at speed maybe not really. So you don't want to necessarily take a power measurement, right? You may not be consuming all that much power. So you may not want to take a power measurement. So practically, right? So sort of more common way of doing this is to do a voltage current measurement. It's basically voltage measurement. Okay. So what happens as the battery degrades, the voltage when you discharge it appears, when you discharge it, basically sometimes looks like a voltage source is outputting power. And that voltage appears to be lower and lower as a capacity phase. Okay, so often you estimate by measuring that voltage in your battery, right? In your battery. This is not very accurate. Okay, this is not terribly accurate. Voltage depends on the battery chemistry, on the capacity, in complicated ways. But nowadays, a lot of the management software, management system on your batteries takes this voltage measurement. And so we know this is not accurate. So this is normally a very conservative measurement. Right? This is very conservative. So if you follow news for Tesla, for example, I think last year or the year before, there was a hurricane on the East Coast. And then basically what Tesla did is they pushed updates to their batteries. And suddenly all the Teslas has 50 miles more range. Okay, so there's hurricane coming, the people figure out they need to get away, and then Tesla through a firmware update suddenly give you 50 miles more of range. Because sort of the way you're estimating range, in electric vehicle range, in this case capacity, as you're being very conservative, it's sort of this underestimate. Right? So there has some headroom. So in emergency, you can use more capacity. But then of course, efficiency-wise, you don't want to leave money on the table, right? So if there are 50 miles, I can squeeze out this battery. I want to squeeze out, maybe in non-emergency situation as well. Okay, so slow cycling is sort of the most accurate way. Just cycle very slowly. You basically the voltage goes down very slowly, and you can measure how much you have. If you just look at a voltage at any one time, that gives you a crude estimate, but may not be very good. Anybody know another way people are thinking about? Maybe without using a battery cycler, without cycling, give the battery to somebody for 2 days and let them cycle it. Anybody heard of some other ways to do this? Okay, so another way we have to do this is acoustic imaging. Okay, so our acoustic measurements. Okay, so you can think of this as your X-ray for your battery, except we're using acoustic frequencies. Okay, so we're using acoustic frequencies. You can think of this as for imaging the battery through acoustic frequencies. And this can give you an accurate picture of the internal chemistry, and hence the capacity and degradation, everything of the battery, if you put into acoustic chamber. So this is also a technology a lot of people are trying to commercialize right now. Okay, so there's different technologies. And a lot of times in practice, is sort of figuring out the capacity is non-trivial. So if you have a great way of doing this, you can potentially make a lot of money in this space. Right? So we often get batteries from King County Metro saying, okay, I have a bus, this battery run for a while, reach the end of life, but we think there's still 70, 80% in it. So maybe take and do something else, right? Do demand response or use as backup. The hardest thing to use as secondhand batteries is actually figuring out how much capacity it has. You often don't know. You got a battery, you often have no idea what is left in this battery. And if we're going to cycle every battery from a bus we get through 2 days spare capacity, we don't have that many cyclers sitting around. Right? So this is an important issue for us to use batteries. When you put batteries into applications, there is always consideration of if you need to figure out the exact capacity, that may be challenging. There's a lot of innovation both on the chemistry side, right, and on the sort of imaging acoustic side, and on the sort of electrical engineering and the algorithm side, trying to figure this out. There's quite a number of things going on in this front. Okay, so there's just something to know about the capacity of the battery. Right? So when we write problems, we write a capacity, but it's often not that simple. Okay, so it's good to keep in mind. It's not quite so simple. All right, so after all this, if we write this, in actual problem, right? If we write this in the actual problem, then normally what we have, the sort of typical formulation works out this way. A typical formulation works out to be. So for example, for using battery, we always want to minimize some cost. This cost may be using the the degradation cost of the battery plus the cost of getting electricity from somewhere else, and things like that. So this is sort of objective function. Right? We want to minimize some objective. So think of battery in a building. The building can decide either to pull power from the battery or pull power from the grid. There's different costs associated with it. And this sort of decision-making problem we have. And then the constraints we have as normally. And so I will write down the constraint, I'll explain this constraint. So this PT is the power in or out of battery. Okay. So what does PT plus mean? This is discharging. Charging. Okay, so this is saying that the total, the net power coming out of the battery is charging and discharging. Then we have one of them has to be 0. Right, so one of them has to be 0 because the battery cannot charge and discharge at the same time. Okay, so it's normally not allowed for your battery to do both operations at the same time. So this sort of doesn't make all that much sense in problem formulations. Okay, so one of them is 0 at this point. Then the time evolution of the battery is okay. So this what means this is so the variable here are ET. This is the energy in the battery, how much energy you have, and the eta. This is the efficiency. This is efficiency. So when you're discharging, you're dividing by efficiency, right? So efficiency, this is some number between 0 and 1. You're dividing by this means that it takes more, right? So the power you actually inject to the grid, for example, is less than the power you pulled out of the battery because there's efficiency. And similarly, when you're charging, you're multiplying by because the power you got from the source, from the grid, let's say, some of these is lost in efficiency. Okay, some of this is lost. Okay. So this is the evolution we have. And then we have sort of different bunch of constraints, right? We have, since we take one to mean charging, one to mean discharging, it should be positive. The energy in the battery should be positive, right? The battery can be empty, that means the energy is 0, right? So it has to be positive. Of course, these are limited by the maximum power injection rate, maximum power rating we allow. And the battery, of course, has a maximum for energy rate. So when you write this into power system problems, power system operation problems, it looks like this. Okay, so when you write them in, it looks, the optimization problem comes down to something like this. Okay, so this is a fairly simple constraints, right? Capture battery. And if you take this, for example, 554, then you can put these into the optimization problem and you can solve the optimization problem. Okay, so this is sort of operationally or algorithmically how we think about battery. We have something that can exchange energy basically over time with some efficiency, and then face a lower upper bound in power and energy. Any question about this? Okay, so next, if you look at again degradation, so this is just looking at degradation more closely. right? Again, for different charging rate, right? So what this says is the degradation is really complicated. Okay, so degradation is complicated. When we normally formulate this kind of problems, we don't use very complicated degradation models because that makes the problem hard to solve. And solving this problem there is still there's still a lot of open problems. Basically, when we try to solve this problem, when we solve this optimization problem with realistic degradation. So what are realistic degradation? Well, for example, if you look at the graph on the left, cycling a battery at different C rates. Yeah, different C rates. So a battery cycled at a high C rate will degrade much faster than a battery cycle at the low C rate, even if they undergo the same number of cycles. Okay? So that means sort of the degradation is not just a function of how many cycles you undergo, it's also a function of how aggressively you cycle the battery, you charge and discharge the battery. So that's a complicating factor. That's where normally it's hard to take that into account for us. Yeah, so it's not linear on how fast you charge the battery. And then the right figure is also sort of depends on the SOC, right? Where you balance the battery at. Okay, so when you charge a battery, normally what you have is, if you have a battery, this is 0 to 100% full. No, for the health of the battery, you normally do not want to charge it. You don't want to leave the battery very close to 100% or leave the battery very close to empty. That's normally not very good for the health of the battery. So normally what you want is you want the batteries to operate in some region, let's say between 40 to 80%. For the health of the battery, you want to be 40 to 80%. So this is another consideration we have. So all these are complicating factors, and all this is making battery not as simple to use as we would like. Okay, so if you naively pretend the battery is a black box and just use the battery that way, then what you quickly figure out is after a year you don't have a battery anymore. Okay, so the battery doesn't work anymore after a year because maybe you did not get the state of charge correct or charge and discharge too aggressively. So what's mostly preventing us from battery to make money nowadays? There's a lot of operational consideration. Right? Basically, what the battery wants to do is it wants to sit at 50% charge all the time. It doesn't want to be charged, doesn't want to be discharged, it doesn't like to be very full nor very empty, so it likes to sit at 50% and not do anything. And that's best for battery capacity. But then obviously that's not a very useful battery. So right now the trade-off is always how do you make it more useful application-wise, and how do you not kill the battery in a very short amount of time? And so that's sort of that's sort of the current question that we're facing when we use a battery in practice. And we're still not terribly good at it. So we want to make money out of batteries, not so easy. It's not so trivial to do today. Okay. And again, so the reason we say, if you operate very aggressive, you don't have a battery, is battery basically have a warranty. And if you stay with the limits in the warranty, then nothing, basically sort of the manufacturer guarantees nothing bad will happen. If you go outside the limit of warranty, then if the battery catches fire, it's your problem, not the manufacturer's problem. But normally people are very careful to operate within the warranty, right? Lifetime warranty of the battery. But that can be very limited. You think you bought a big battery, at the end of the day, you may only have 20% of the battery to use. Okay, so that's expanding this warranty is a lot of research on, say, chemical engineering and the material science engineering. And now the electrical engineering side is, given these are the limitations, how do you best use a battery? Okay, how do you best use a battery? Right? Okay, so this is the operations. So we'll see more of this in the next lecture when we talk about, right? So how do you, when you put this kind of problems into optimization framework, how do you think about this? So we'll see more of this. We'll see more of this issues. But today, to finish, I want to look at sort of a little bit more chemistry of different kind of batteries and what happens, and so what's the advantage and disadvantage of different types of technologies. Okay. So this is a picture of lithium ion battery. So the reason lithium ion battery, sometimes catches fire and we have safety hazard and the capacity degrades, as when you use a battery, you basically see a lot of these sort of defects start to build up within the battery. Okay, so you have a cathode and anode, right? You have two polarities, two poles. And then when you use the battery, basically what happens is you start to build this sort of dendrites in the battery. And so you build this sort of little bit dendrites in the battery. And this comes from the fact that things calcify and the solution, right? Basically, you calcify and it's not as efficient as before. So things stick around and they don't move anymore. And then the reason why this can lead to fires and stuff is because this can potentially short. Okay, so what this can do is this can potentially short out the battery. Okay, so if there is a path, right, so if this ever touches, right, then this creates a path going from the positive to negative potential. Okay, so this is, let's say this is the cathode, this is anode. If this touches, this shorts a battery. Okay, this shorts a battery, and then the battery catches on fire. Basically, you're shorting, power and ground. Basically, you're shorting sort of source and ground. Okay, so this degradation in lithium ion battery, this tends to, this may short out the battery. So this can short the battery. Okay, and this is the degradation is basically this kind of growth defect as you use battery. Okay, so you have this sort of growth defect when you use battery. So this is the imaging, right? So if you can take the battery, take it apart and do imaging, then we can see it. But the challenge today is if you don't do this type of imaging, how do you characterize this? And how do you make a battery that has less dendrites, right? Okay, so these are the questions we have. People are thinking about for lithium ion. Then if you look at, so lithium ion has this kind of issue. So you can ask the question, can we think of battery, maybe the degradation is not so bad, right? Can we think of battery, maybe degradation is not a huge issue? And that's the flow battery we have. So I'm not going to pretend to understand what the actual solution is in the flow battery, but the way this works is you have a tank. Okay? What you have is you have a passive electrode. Okay, so you have a tank that carries some electrolyte. Okay, so there's some electrolyte tank. And then what you do is you have a pump. Okay, so you pump the electrolyte, and electrolyte basically cycles. So there's an exchanger in the cell. So this is actually the cell. And then there's a positive electrode, there's a negative electrode. Right, so this is, of course, goes into a, let's say, converter. If converter and goes out to the grid, and you have a negative electrolyte. And you have another pump. Okay. So the way this thing works is as long as you pump electrolytes into the cell, they will react and they'll create a potential difference. Okay, they'll create a potential difference. And then you can generate electricity that way. Okay, so there's no sort of metal ion involved. per se, right? So this flow battery. And the good thing about this flow battery is this is very low degradation. Because you don't have this kind of sort of non-reversible buildup. Okay, the problem with lithium ion degradation is not reversible. Right? Once it builds up, it's very hard to get rid of. Whereas in this flow battery, you're pumping everything around, and you can actually, as long as you pump them around, I think in practice is you have very low degradation. And so almost as if you have, no degradation in the battery. The capacity does not drop as you use the battery. Okay? You don't have, chemically all the. So I think chemically the reason is everything here is reversible. Okay? So easily reversible processes. So there's no permanent buildup of defects and things like that. The drawback of this is sort of the power rating. Is lower because you have to pump things together, right? So you have to mechanically pump fluid into a cell. So that may take some time for it to get going. Okay, so in very high power requirements, this may not be possible. Okay, this may not be possible. And obviously, in application like cell phones and laptops, this is not competitive, right? So we are not. It's hard to imagine doing this for a cell phone. Okay, so that's not competitive. But in some other applications, for example, let's say using battery as a backup for a building or for a data center or for some other critical infrastructure, then this is seen being quite flexible, because you have no degradation. You can actually store the electrolytes far away. Okay? So the cell can be quite small, as long as you have tanks that can store things far away. Then they can react in a small cell that can produce electricity. That's not an issue. So not everything has to be, together at the same time. This is hard to catch on fire because you're limited by the flow rate. So you can engineer valves and things to limit the flow rate. You can catch on fire. Whereas lithium ion, you can catch on fire because once you short, then all the energy can be discharged. You can't limit energy once you short the battery. But here, even if things short, let's say they mix in such a way, all you do is you cut the flow, and then that limits the energy that's available, right, to the short. Okay? So it's safer in that regard, right? So but then they also the drawbacks, the electrolyte themselves may be chemically unsafe. So you may have to build sort of special housing units for these. Okay? So there's sort of a bunch of positive and negatives. But this is being talked. But this is sort of being talked about as a competitor, and this is in some areas competitive with lithium ion. So it's unclear, whether in 10 years, which one of these will use in, say, building applications. Will still be lithium ion batteries, will be flow batteries of this type. Okay. Another thing I want to finish today with the supercapacitors. Yeah, supercapacitors. So supercapacitor is just a big capacitor. For you mentally, what you want to think of this as a huge capacitor. Okay, so think of this large capacitor. What a supercapacitor? What's the problem with this thing? This has a long lifetime. Can operate actually for many cycles. So million cycle lifetime. This capacitor, this supercapacitor. This can charge and discharge quite fast. Fast charge and discharge. It's again, it's a capacitor. It's not. There's no moving parts to this, right? But the drawback of this sort of has high self-loss. So what this means is the capacitor sits there, you lose the energy quite quickly in this capacitor. Okay, so capacitors are storage elements, but capacitors tend to discharge. even if you just leave it there. Okay, so it has this sort of high self-loss. So this is only suitable, so this is more suitable to places where you need to store energy for a short amount of time. And not for hours, but a short amount of time. And this has applications in wind turbines. Okay. So before we said we're dumping power, right, through a resistance in wind turbine over a few seconds. Oh, sorry, not over hundreds of milliseconds. So you can replace that resistance, for example, use a supercapacitor. Okay, so instead of dumping things to a resistor, you can dump it to a supercapacitor. And then if the fault clears relatively quickly, you can recycle the power back to the grid. Okay, so you don't have a loss, right? The power is still, most of the power still went to the grid. Okay? So this is technology you see in wind turbines. Sometimes instead of a resistor bank, you have a supercapacitor bank. And the hope is if the fault clears fast enough, this energy can now be routed to the grid again. Okay? So these are all possibilities, right? So the different technologies. Okay? Right, so we'll stop here today. The next class, we'll start to put all this together. We'll run have some more numbers, do some calculations with batteries, and say, economically how to make a decision, what makes sense, and how should you use batteries. Okay, we'll look at that more in an optimization and control method. So today is mostly about chemistry. Next class will be more operations, right? So the last week of class. Okay. So I'll see. So we'll have a short homework. It will be posted tonight or tomorrow. So that'll be due. Instead of Wednesday, I'll have it due the end of next week. We'll have a short homework, looking at batteries and some conceptual questions. Okay. So no questions. I'll see you next week.
Thank you.